A very good morning to everyone present here and fellow cohort members. It is our pleasure to be presenting our final project, the Hyperion 1, the experimental rocket we crafted over the weeks of this awesome program. We have put a lot of effort into making this rocket. We hope you all enjoy listening to this. Without further ado, let's begin. Starting off, we have our incredible team led by our super cool mentors Mahesh sir and Lakshesh sir. We thank them for all the guidance and support. Over the course of the program, we divided into subsystems teams, which are as follows. We divided into structural systems design team, propulsion systems design team, recovery systems design team. In the structural systems team, we have Yash, myself, Kashika, and Anjalika. In the propulsion systems team, we have Satyam, Tanmay, and Amog. In the recovery systems team, we have Bharati, Suhani, Ishita, Aryan, and Nishant. These are the main topics we will discuss today. Mission statement, high power rocketry, design of the rocket, subsystems, and at the end, a Q&A session. Our mission statement is to design an experimental rocket that flies to an altitude of 10 kilometers and will carry a payload of 500 grams. What is a rocket? A rocket is a vehicle that is used for transportation. It uses the law of conservation of momentum for propulsion. Our mentors taught about these laws descriptively in the first few weeks of the program. Next, we have high power rocketry by Aryan. Over to you, Aryan.
I'm Aryan and I'm going to be talking about high power rocketry. Unlike the model hobby rockets, experimental rockets use components which are built from scratch. The high-power rockets, which are similar to experimental rockets, use rocket motors which are available commercially. Due to the lack of rules and regulatory bodies in India, experimental rocketry is quite a challenge. The experimental rocketry is advantageous in getting hands-on experience of building rockets that can reach higher altitudes. Rocket motors, which exceed model rocketry motor definitions, and the models that use these motors are collectively referred to as high power rocketry. Short form HPR. HPR is similar to model rocketry with differences that include the propulsion power and weight increase of the model. They use motors in ranges over G power or way more than laws and regulations allow for unrestricted model rockets. Rules for making a rocket. A rocket exceeds the definition of a model rocket under NFPA 1122 and becomes a high-power rocket under NFPA 1127 if it uses a motor with more than 160 Newton-seconds of total impulse. The other rules are given here. Over to Amol.
Thanks, Aryan. Hey everyone, I will be explaining about the open rocket design. This model is in accordance with our mission statement as it is capable of going up to an altitude of 10 kilometers. Here is the 3D finished model of the rocket. Moving ahead, this is the simulation of the rocket which gives us very important values like altitude, vertical velocity, vertical acceleration, which were used by the structural team to design it in CAD. Over to you, Yash.
Hello everyone, I am from the structural team and I will talk about the structure we built. So we basically designed the anatomy of our rocket, and this is the initial design which we built, named it as Hyperion 1. This was built using a software called CAD software on chip, which is very collaborative. So these are the basic parts which we are going to use in our rocket. First is the nose cone. The nose cone plays a vital role during the journey. Due to its aerodynamic shape, it helps the rocket to prevent air friction from slowing the rocket. Next are the fins. The fins help us to guide the rocket fly straight. The fins, speaking about fins, it helps to control the rocket. Next are the body tube. Body tube forms the main body of our rocket, and which connects the nose cone from the top and the fins at the bottom. Next is the tube coupler. The tube coupler joins the two body tube together and strengthen the rocket. Over to you, Satyam.
All right, sorry, due to technical difficulties, I'll be continuing Satyam's part. So, I'm here on behalf of the propulsion team to tell what all we have learned and how we applied that knowledge to make our rocket engine. We're using a solid rocket engine because it is mostly used in an experimental rocket and it is easy to design. Since commercial rocket engines are not available for sale in India, we had to design our own engine from scratch. And to design our engine, we used the Open Rocket tool. So there are three main components of our engine. Starting off with the motor casing, it acts like a pressure vessel or combustion chamber, you could say, for a solid rocket engine. It also acts like a propellant tank where it stores the solid propellant in form of fuel grains. Second is the bulkhead. It seals the motor casing so that the gases exit from one side only. It houses the igniter, which is responsible for the beginning of the combustion in the engine. The bulkhead's outer curved surface area is polished and it is attached to the motor, causing by hammering 8 screws. Next is the O-ring, which is a rubber ring which seals the gaps in the bulkhead. There are 2 O-rings present to provide more redundancy. Third one is the nozzle. It accelerates the gases coming out of the combustion chamber, thus providing more thrust for liftoff. Through it is a small cross-sectional area present between convergent and divergent sections of the nozzle. The nozzle is attached to the motor casing by hammering 8 screws. The O-rings in the nozzle also serve the same purpose as they serve in the bulkhead. Now for the propellant, we are using APCP, otherwise known as ammonium perchlorate composite propellant, which uses aluminium powder as fuel, ammonium perchlorate as oxidizer, and HTBP as binder. In the slide is given the physical properties of APCP. Also, we are using a tubular grain profile because it provides progressive thrust time curve. In this table that you see on the slide, the specifications of the engine we have designed are given. It contains all the assumed and calculated values of the physical quantities which we are required to have while designing the engine. Thank you, and over to Sahani.
Hi everyone, I will be explaining the electronics and the basic recovery of the rocket. So what is recovery? Recovery is the process of getting back to the object's original state. In this case, recovery means to regain the rocket after it has reached the ground. Why do we need recovery? Well, we need recovery so that we don't have to remake the entire rocket, but with just a few modifications, use it again, such as replace the engine and refill the fuel, and voila! Your rocket can be used again. The electronics we will be using in our rocket are 2 altimeters and the flight computer. The flight computer is going to be used for taking updates from the rocket, such as the altitude, fuel capacity, temperature, and is also going to be used to launch the rocket and deploy the parachutes. The electronic deployment system has commands that are set prior to the launch of the rocket. When the rocket reaches the apogee, the chip will deploy the drogue chute first. And after reaching the average of 500 to 700 feet, it will deploy the main chute. Over to you, Bharati.
The most popular parachutes used for rocket recovery is the cruciform chute that's shaped like a cross, flat sheet chutes that deploy from the top of the flight, and the panel chute and the elliptical and spherical chute. Each shape has its own advantages and disadvantages. The important thing we look for in the shape is if it suits our rocket's mass and the shape's stability at apogee, and the materials were chosen carefully too. We are using the cruciform chute as a main chute, the elliptical chute as the drogue chute due to its protective frontal area and good stability. There are 3 ways of packing the parachute inside the body tube: the traditional fold and wrap, the deployment bag, and the pressure pack. The traditional fold and wrap is the most common method used by most rocketeers for its simplicity. Deployment bag used is for the larger chutes, where it is fitted inside a tight space. By following a simple technique, it is easy to get a consistent packing density and a reliable deployment without tangles. The pressure pack is the most extreme method of packing a chute, as it has by far the highest packing density. The military and many aerospace deployment systems use this. The 3 most used ways of using of deploying the parachute is the black powder ejection system, the CO2 ejection system, and the integrated system. The black powder is easy and reliable, but sometimes the heat can damage the fragile nylon canopies, due to which we use ripstop nylon canopies. CO2 systems is clean and reliable. It doesn't damage your parachute and it can be used at high altitudes, but it has to be designed carefully because of the pressure that has to be managed. Integrated system is very compact and highly reliable. It needs special equipment to pack the chute. Over to Nishant.
Hello everyone, let's get into the specifications of the parachute. The drogue chute and the main chute both are made up of ripstop nylon. We choose ripstop nylon because it is strong and even if there is a hole in the parachute, it won't expand. The shape of the drogue chute is elliptical and the main chute is cruciform in shape. These shapes are the most preferred as they provide more surface area and reduce the descent velocity. We calculated the diameter and surface area of the parachute according to the mass of the rocket and descent velocity of the rocket. The descent velocity of the rocket is 5 meters per second. The surface area of the main chute is 6.79 square meters and the surface area of the drogue chute is 5.26 square meters. The mass of the drogue chute is 60 grams and the main chute weighs 396 grams. The packing volume is the area occupied by the parachute when it is packed inside the rocket's body tube. The packing volume of the drogue chute is 158.4 cubic centimeter and the main chute is 1070.3 cubic centimeters. The hole in the drogue chute is called spill hole. It stabilizes the rocket while descending. Over to Ishita.
Black powder ejection system is used to eject both the parachute. At the apogee, the drogue chute is deployed as a result of the ignition of the black powder, also called the gunpowder. At an optimum altitude, the main chute is deployed in the same way. The black powder is stored in a small metallic tubes attached to the coupler, which also has an EMAX or an igniter attached to the flight computer. The burning of the black powder produces immense pressure to deploy the parachute. The amount of black powder required as per our calculations are 1.48 grams for the drogue chute and 3.42 grams for the main chute. These are the parachute and ejection charge we are using in our rocket. Over to you, Fida. Thank you, Ishita, for the wonderful explanation. This is our final rocket model. The pictures you have seen before was the initial design. Later, we decided to go with dual deployment. What's next? The team is planning to take this project further and maybe hold a crowdfunding, get all the parts for the rocket, and then assemble it. For the time being, we have placed a dummy mass for the payload, but we plan on replacing it later with a scientific fuel or something as such. With that, we have come to the end of our presentation. I hope you all enjoyed our presentation. Now we have the Q&A session. If you have any questions you would like to ask, please post them in the link posted in the chat. Thank you.
So he wants to know whether the system that you have designed is it a single stage system.
So I would like to take up the question. I worked in the structural team and no, it's not. It is a single stage rocket. It is not a two-stage rocket. We just have two body tubes which you have connected with a tube coupler. I hope that answers your question.
In the recovery, if the parachute breaks, what alternative you have to prevent any damage to people or objects on Earth?
I'd like to take up this question. So basically our parachute, we have programmed the flight computer as such that suppose the drogue chute is stuck at the apogee, it is programmed to deploy the other main chute. And suppose, so basically we have these alternatives that are there and we're still working on it.
Railgun, electromagnetic launcher, or space elevator, or even laser, like pushing with the laser. You can read about it because chemical propulsion is really extremely inefficient, yes. And even, for example, the payload mass fraction of launching to the space shuttle, the actual payload is only 1%. payload means astronauts or equipment. The rest of the mass most of it is in the fuel. So
Yes,
that's called the tyranny. That's called the tyranny of the rocket equation. You can look on the there's a nice article written about it. It's called The Tyranny of the Rocket Equation. Just look at it on Google. You'll have fun reading it.
All right, ma'am. We'll research more on it. Thank you for the suggestion, ma'am. We'll definitely look into it.